So let's forget about this example and review what we learned in 11.3, chapter 11. Chapter 11 again was functions of several variables. In our case, I'll say functions of two variables. .3 taught you what? Taught you some beautiful things. Practically, if you understand this picture, you will remember everything. This picture is going to try and consider a graph that's sitting above here somewhere in the Euclidean 3 space, two-dimensional space. You have the origin, and you say, I want markers. No, you don't say I want markers. I say I want markers. We want to fix a point, x0, y0 on the surface, assuming the surface is smooth. That x0 of mine should be projected. I'm going to try to draw better than I did last time. x0, y0 corresponds to a certain altitude, z0. That is projected like that, and this is my z0 here. But I don't care very much about that right now. I care about the fact that locally I represent the function as a graph, z of f of x and y defined over a domain. I have a domain that is an open set, simply connected. That's more than you need to know. Could be anything. Could be a square, could be a this, could be something, a nice patch of the plane. So the projection of my point here is x0, y0. I'm going to draw these parallels as well as I can, but I cannot draw very well, but I'm trying. x0 and y0. And remember from last time, what did we say? I'm going to draw a plane of equation x equals x0. All right, I'll try and do a good job. X equals x0 is this plane.
Don't you have the x naught and the y naught backward? Or
no?
Is x?
X is this one.
Well, yeah.
Coming towards you like that. And I also think about that always, Ryan. Do I have them backward? This time I was lucky. I didn't have them backward. So y goes this way. For y0, let me pick another color, a more beautiful color. For y0, my video is not going to see the y0, but hopefully it's going to see it. It's a beautiful line. Spring is coming. So this is going to be the plane. Label it Magdalena y equals y0. Now the green plane cuts the surface into a plane curve, of course, because it is in the plane that I drew with lime. And in the plane that I drew with red, was it red or pink? Oh, it's Valentine's, it's pink. Okay, so I have it like that. So what is the pink curve? The pink curve is the intersection between x equals x0 plane with my surface. My surface is black. I'm going to say S from surface. And then I have the pink curve. Let's call it C1 because you cannot see pink on your notes. Well, you can imagine, but it's not the same thing. C2 is y equals y0 plane intersected with S. And what have we learned last time? Last time we learned that we introduced some derivatives at the point x0, y0 so that they represent those partial derivatives of the function z with respect to x and y. So we have the partial z sub x at x0, y0, and the partial z sub y at x0, y0. Do we have a more elegant definition? That's elegant enough for me, thank you very much. But if I wanted to give the original definition, what was that? That is df dx at x0, y0, which is limit of the difference quotient. This time I'm not gonna do delta x delta y. I'm different today, so I do h goes to 0. H is my small displacement that goes to 0. I have f of, now, who is the variable? X. So who's gonna stay fixed? Y. So I'm gonna say I'm displacing Mr. X0 with an h, and y0 will be fixed, minus f of x0, y0 all over h. So again, instead of a delta x, I call that h, and the derivative with respect to y will assume that x0 is a constant. I saw how well Khan Academy explained that, and I'm ambitious. I want to do an even better job than they do. Hopefully I might manage. df dy, so y0 equals limit h going to 0 of, let's see, f of, now who's telling me what we have? Of course, Mr. xy and y. It's f of x0, y0 is there, constant, waiting for his turn. H is your parameter, and then you have what? X0 is fixed, right? So x0 is fixed. Y is the variable. So I go into the direction of y, starting from y0, and I displace that with a small quantity, right? So these are my partial velocity, my partial derivatives. I'm sorry, not partial velocities. Forget what I said. I said something that you will learn later. What are those? Those are the slopes at x0, y0 of the tangents at the point here. Okay? The tangents to the two curves, the pink one and the gray, then the green one. All right. For the pink one, for the pink curve, what is the variable? The variable is the y, right? So this is C1 is a curve that depends on y, and C2 is a curve that depends on x. So this comes with x0 fixed. I better write it like that. F of x0 y, and instead of C2 of x, I'll say f of y, f of x and y0. So which slope is which? The df dy at this point is the slope to this one. Are you guys with me? The slope of that tangent. Considered in the plane where it is. How about the other one? F sub x will be the slope of this line in the green plane. Okay? That is considered as a plane of axis of coordinates. Good. Good. So we know what they are. A quick example to review. I've given you some really ugly, nasty functions to derivate last time, and you did a good job. So today I'm not challenging you anymore. I'm just going to give you one simple example. And I'm asking you, what does this guy look like, and what will the meanings of z sub x and z sub y be? What will they be at? Let's say, I think I know what I want to take at the point 0, 0, and maybe you're gonna tell me what those will be, and eventually at another point like z sub x, coordinates 1 over square root of 2 and 1 over square root of 2, and z sub y the same. 1 over square root of 2, 1 over square root of 2. Can one draw them and have a geometric explanation of what's going on? Well, I don't want you to forget the definitions, but since you absorb them with your mind, hopefully, and your eyes, you're not going to need them anymore. We should be able to draw this quadrant that you love. I'm sure you love it. What is that? What does it look like? Wait a minute. You're not awake. I'm not awake. So if it were x squared plus y squared, don't write it down, please. It would be that. And what is this?
That's a reflector.
A circular parabola. You're correct. We've done that before. It's it looks like an eggshell, but it's actually this is a parabola. It's going to infinity. And you said a bunch of circles. Yes, sir.
So is it upside down?
It's an upside down paraboloid.
Translated.
So it's very good. How do we do it? We make this guy look in the mirror. This is the lake. The lake is XY plane. So this guy is looking in the mirror. Take his image and shift it just like he said, shift it 1 unit up. This is 1. You're going to have another paraboloid. So from this construction, I'm going to draw, and it's going to look like you took a cup and you put it upside down, but it's more like an eggshell, right? It's not a cup, because a cup is supposed to have a flat bottom, right? But this has it's like an eggshell. And I'll draw, and for this fellow we have a beautiful picture that looks like this, hopefully, but I'm going to try to draw.
And you look at from the top to bottom?
We can look at wherever you want to look. That's a very good thing. You're getting too close to what I wanted to go. We'll discuss in a minute. So, you can imagine this is a hill full of snow, although in 2 days we have Valentine's Day, so it's not, there is no snow. But assume that we go to New Mexico and we find a hill that more or less looks like a perfect hill like that, and we start thinking of skiing down the hill. Where am I at 0, 0? I am on top of the hill. I'm on top of the hill, and I decide to analyze the slope of the tangents to the surface in the direction of, who is this? Like, now, Ryan, you made me nervous. So in the direction of y, I have one slope. In the direction of x, I have another slope in general. Only in this case, they are the same slope. And what is that same slope if I'm here on top of the hill? This is me. Well, I don't know. One of you guys. That looks horrible. I mean, what's going to happen? We don't want to think about it, but definitely it's too steep. So this will be the slope of the line in the direction with respect to y. So I'm going to think f sub y and f sub x if I change my skis into this direction and I go down. So I could go down this way and break my neck, or I could go down this way and break my neck as well. Okay. It has to go like that. Right? Can you tell me what these guys will be? I'm going to put them in pink because they're beautiful.
0.
Thank God, they're beautiful. What does it mean? That means that the two tangents, the tangents to the curves are horizontal. And if I were to draw the plane between those two tangents, one tangent is in pink and one is in green. Today I'm all about colors. I'm in a good mood. And that's going to be the so-called tangent plane. Tangent plane to the surface at x0, y0, which is the origin. That was a nice point. That is a nice point. Not all the points will give you a nice, beautiful result. I picked a nice, well, not so nice, I don't know. You'll have to figure it out. How do I get, well, first of all, where is this point? If I take x to be 1 over square 2 and y to be 1 over square 2, and I plug them in, what's z gonna be? 0, and I did that on purpose. Because in that case, I'm gonna be on flatland again, it just look like Lubbock. Except Lubbock is not z equals 0. What is Lubbock like? Z equals, do you want to go in meters or in feet?
Is it only about a mile? It's about a mile.
Yes, I don't know. I thought it's about like 1 kilometer, 1,000 something meters. But somebody said it's more, so it's flat land at, so I'd say about a mile above the sea level. All right. Now, I'm gonna be in flat land right here. 1 over root 2, 1 over root 2, and 0. What happened here? Here I just already broke my neck. No. Well, if I came in this direction, I would need to draw a perspective trajectory. That was hopefully not mine. And the tangent would, the slope of the tangent would be funny. Let's see what you need to do. You need to say, okay, prime with respect to x, minus 2x, and then at the point x equals 1 over root 2, y equals 1 over root 2, you just plug in, and what do you have? Negative square root of 2. Oh my God, that is really bad as a slope. It's a steep slope. And this one, how about this one? Same idea, symmetric function, and it's going to be exactly the same. Very steep slope. Why are they negative numbers? Because the slope is going down. So that's the kind of slope I have in both directions. One and the other. All right. If I were to draw this thing continuing, how would I represent those slopes? This circle is just making my life harder, but I would need to imagine those slopes as being like, I'm here, all right? Are you guys with me? And I would need to draw x, 0. Well, what is that? 1 over root 2 and 1 over root 2. And I would draw 2 planes, and I would have 2 curves. And when you slice up, imagine this would be a piece of cheese.
Right here?
And you cut.
Right in the middle.
Right?
Yeah.
And you cut in this other side. Well, this is the one that's facing you. You cut like that, and when you cut like this, it's facing
You will see the angle only.
But anyway, let's not draw the other one. It's hard, right?
If you
So-
see the angle like this, just a piece of it, the corner of the cheese.
Right.
The corner is facing you.
So yeah, so it's the corner is facing you.
So basically you will
here,
see this
but exactly. But
like this.
yeah, well, yeah, it's hard to draw. So practically, this is what you're looking at, a slope that's negative in both directions. So you're going to go this way or this way, and it's much steeper than you imagine. So, okay, they are equal. I'm trying to draw them equal. I don't know how equal they can be. One belongs to one plane, just like you said, this belongs to this plane, and the green one belongs to the to the plane that's facing you. So the slope goes this way, but the two slopes are equal. You have to have a little bit of imagination. We would need some cheese to make a mountain of cheese and cut them and slice them
Bring some
and
jelly.
eat everything after. Yeah. All right. Let's move on to something more challenging now that we got to the tangent plane. So if somebody would say, wait a minute, you said this is the tangent plane to the surface. You just introduced a new notion. You were fooling us. I'm fooling you guys. It's not April 1st, but this is kind of not a neat thing. I just tried to introduce you into the section 11.4. So if you have a piece of a curve that's smooth, and you have a point x0, y0, can you find out the equation of the tangent plane? Pi, and this is S from surface. How can I find the equation of the tangent plane? At x0, y0, well, it's going to be also z0, but what I mean that x0, y0 is on the floor as a projection. So I'm always looking at the graph, and that's why. The moment I stop looking at the graph, things will be different, but I'm looking at the graph of independent variables x, y, and that's why those guys are always on the floor. A and z will be a function, the dependent variable. Now, does anybody know, because I know you guys are reading in advance and you have better teachers than me, you have the internet, you have the links, you have YouTube, you have Khan Academy. I know from a bunch of you that you have already gone over half of the chapter 11. I just hope that now you can compare what you learned with what I'm teaching you. And I'm not expecting you to go in advance, but several of you already know this formula. We talked about it in office hours on yesterday, because Tuesday I didn't have office hours. We had a coordinator meeting. So, what equation corresponds to the tangent plane? Several of you know it. You know what I hated? It's fine that you know it. I'm proud of you guys, and I'll write it, but when I was a freshman, or what the heck was I, a sophomore? I think, no, I was a freshman when they fed me, they spoon-fed me this equation, and I didn't understand anything at the time. I hated the fact that the professor painted it on the wall, on the board, just like that out of the blue. I wanted to see a proof, and he was able to, I think he could have done a good job, but he didn't. He showed us a bunch of justifications, like if you generally have a surface in implicit form, I told you that the gradient of f represents the normal direction, right? And he prepared us pretty good for what could have been the proof of that. He said, okay guys, you know the direction of the normal as given as the gradient over the length of the gradient if you want unit normal. How did he do that? Well, he had a bunch of examples. He had the sphere. He showed us that for the sphere you have the normal, which is the continuation of the position vector. Then he said, okay, you can have approximations of a surface that is smooth and round with osculating spheres, just the way you have for a curve, a best fitting circle, that's called osculating circle. Best fitting circle. In that case, what will the normal be? Well, the normal will have to depend on the radius of the circle. So you have a principal normal, or a normal if it's a plane curve, and it's easy to understand that's the same as the gradient. So we had enough justification for the, hey, direction of the gradient of such a function is always normal. Normal to the surface, normal to all the curves on the surface. If we want to find a proof of that without swallowing this like I had to when I was a student, it's not hard. And let me show you how we do it. We start from the graph, right? Z equals f of x and y. And we say, well, Merkelina, but this is the graph. It's not an implicit equation. And I'll say, yes, it is. Let me show you how I make it an implicit equation. I move z to the other side. I put 0 equals f of xy minus z. Now it is an implicit equation. So you say you cheated. Yes, I did. I have cheated. It's funny that whenever somebody gives you a graph, you can rewrite that graph immediately as an implicit equation. So that implicit equation is of the form a big F of x, y, z now equals a constant, which is 0. F of x, y is your old friend, and minus z. Now, can you tell me what is the normal to the surface? Yeah, in a splash, in a minute, like that. So what is the gradient of f? Gradient of f will be the normal. I don't care if it's unit or not, but heck with the unit or normal. I'm gonna say I want it prime with respect to x, y, and z, respectively. And what is the gradient? It is the vector big F sub x, comma, big F sub y, comma, big F sub z. And we've seen that last time. So the gradient of a function is the vector whose coordinates are the partial velocities, your friends from last time. Can we represent this again? I don't know, you need to help me. Who is big F prime with respect to x? There is no x here, thank God that's like a constant. I just have to take this little one, f and prime with respect to x, and that's exactly what that's going to be. Little f sub x. What is a big F prime with respect to y? Little f sub y prime with respect to y. Differentiate with respect to y. And finally, if I differentiate it with respect to z, there is no z here, right? There is no z, so that's like a constant. Prime will give me 0 and minus 1. So I know the gradient, I know the normal. This is the normal. Now, if somebody gives you the normal, there you are. You have the normal to the surface. Normal to surface. What does it mean? Equals normal to the tangent plane to the surface. Normal or perpendicular to the tangent plane. To the tangent plane of the surface. At that point, who is the point? P. Alright? So if you were to study a surface that's around you, do you have a Coke? No. Do you? Okay. Okay. I want to study the tangent plane at this point to the surface. Well, that's flat, Magdalena. You have no imagination. The tangent plane is this plane. It's the same as the surface. So no fun, no fun. How about I pick my favorite plane here, and I take, what is it? Okay. I have this is Children International. I have a little girl abroad that I'm sponsoring. So you have a point here, and a plane that passes through that point. This is the tangent plane. And my finger is the normal. And the normal, we call that normal to the surface when it's normal to the tangent plane. At every point, this is what the normal is. All right, can we write that based on chapter 9? Now I will see what you remember from chapter 9, if anything at all. All right. How do we write the tangent plane if we know the normal? Okay, review. If the normal vector is AI plus BJ plus CK, that means the plane that is perpendicular to it is of what form? AX plus BY plus CZ plus D equals 0, right? You've learned that in chapter 9. Most of you learned that last semester in Calculus 2 at the end. Now, if my normal is f sub x, f sub y, and minus 1, those are ABC for God's sake. Well, good. Big A, big B, big C at the given point. So, I'm going to have f sub x at the given point P times x plus f sub y at the given point P times y. Who is C? C is minus 1. Minus 1 times z. You say, you're being silly, Magdalena. Why do you write minus 1? Just because I'm having fun. And plus d equals 0. And you say, well, wait. This starts looking like that, but it's not the same thing. All right. How do you get to D? Now, actually, the plane perpendicular to N that passes through a given point can be written much faster, right? So if a plane is perpendicular to a certain line, how do we write it if we know a point? If we know a point and the normal ABC, I have to go backwards to read it, not backwards. Then the plane is going to be AX minus X0 plus B times Y minus Y0 plus C times Z minus Z0 equals 0. So who is the D? The D is all the constant that gets out of here. So the point x0, y0, z0 has to verify the plane. And that's why when you plug in x0, y0, z0, you get 0 plus 0 plus 0 equals 0. That's what it means for a point to verify the plane. When you take the x0, y0, z0 and you plug it into the equation, you have to have an identity 0 equals 0. So this can be rewritten ax plus by plus cz, just like we did there, plus a d. And who in the world is the d? The d will be exactly minus ax0 minus by0 minus z0. If that makes you uncomfortable, this is in chapter 9. Look at the equation of a plane and the normal to it. Now I know that I can do better than that if I'm smart. So again, I collect the ABC. Now I know my ABC. I put them in here, so I have f sub x at the point times who? Oh, okay, x minus x0 plus, who is my b? F sub y computed at the point p times y minus y0 and what? Minus, right? Minus 1, I'm not going to write minus 1, you're going to make fun of me. Minus z minus z0. And my proof is done. QED. What does it mean, QED? In Latin. QED means I proved what I wanted to prove. Do you know what it stands for? Did you take Latin, any of you? You took Latin? Quod erat demonstrandum. So this was to be proved. That's exactly what it was to be proved. That what? That z minus z0, which is my fellow over here, pretty in pink, is going to be f sub x times x minus x0 plus f sub y times y minus y0. So now you know why the equation of the tangent plane is that. I proved it more or less, just making some assumptions, some axioms as assumptions, but you don't know how to use it. So let's use it. So for the same valley, no valley hill, it was full of snow. Z equals 1 minus x squared. What was it, guys? I forgot. Okay, no, 1 minus x squared minus y squared. Find the tangent plane at the following points. At x0, y0 to be origin. And you said, did you say that's trivial? Yes, it is trivial, but I want to do it one more time. And at, what was my favorite point before? 1 over root 2 and 1 over root 2. Okay, and what will be the corresponding point in 3D? 1 over root 2, 1 over root 2, I plug in, I get 0. And with this, I hope to finish today so we can go to our other businesses. Is this hard? Now, I was not able, I have to be honest with you, I was not able to memorize the equation of the tangent plane when I was young, like a freshman or sophomore. I wasn't ready to understand that this is a linear approximation of a curved something. It's practically like the Taylor equation for functions of two variables, where you neglect the quadratic term, the third term, and so on. You just take the, I'll teach you next time why this is a first order linear approximation. All right, can we do this really quickly? It's gonna be a piece of cake. Let's see. Again, how do we do that? This is f of x and y. We computed that again. F of 0, 0 was a 0. Guys, if I say something silly, please stop me. F sub x, f sub y at 0, 0 is 0. So I have two slopes. Those are my hands. The slopes of my hands are 0. So the tangent plane will be z minus z0 equals 0. What is z0? 1, excellent. Why is that 1? 0 and 0 give me 1. Okay. So that was the picture that I had z equals 1 as the tangent plane at the point corresponding to the origin. That looked like the North Pole, 0, 0, 1. Okay. No, it's the top of the hill. And finally, one last exercise, and you say, maybe you can do this by yourselves, but I will shut up if I can. I can't in general, but I'll shut up. Let's see, f sub x at 1 over root 2, 1 over root 2. What was that? What is f sub x?
Negative square root 10.
Right, we've done that before. And you got exactly what you said, minus root 2. F sub y at the same point. I am too lazy to write it down again, minus root 2. And how do we actually express the final answer so we can go home and wherever to the next class? Is it hard? No. What's the answer? Z minus, now attention, what is the 0? 0, right. Why is that? Because when I plugged 1 over root 2, 1 over root 2, I got 0. 0. Do I have to write it down? No, not unless I want to be silly. But if you do write down everything and you don't simplify the equation of the plane, we don't penalize you in any way in the final, okay? So if you show your work like that, you're going to be fine. What is that 1 over root 2? Plus minus root 2 times y minus 1 over root 2. Is it elegant? Nope, it's not elegant at all. So as the last row for today, one final line, can we make it look more elegant? Do we care to make it look more elegant? Definitely, some of you care. Z will be minus root 2x. I want to be consistent and keep the same style in y. And the constant goes wherever you want to go at the end. What's that constant? So you see what you have. You have this times that is a 1, this times that is a 1, 1 plus 1 is 2. All right, are you happy with this? I'm not. I'm happy. If this were a multiple choice, you would be able to recognize it right away. What's the standardized general equation of a plane though? Something x plus something y plus something z plus something equals 0. See, so if you wanted to make it very happy, you would still move everybody to the left-hand side. Do you want equal to or minus 2? It doesn't. It doesn't. Negative 2. Is that okay? Is that fine? Are you guys done? Is this hard? It's hard. No. Who said it's hard? So I will work more tangent planes next time. But I think it's something that we can practice on. And do we expect one exercise like that among those, God knows, 15, 16 on the final? I'm not sure about the midterm. I like this type of problem, so you might even see something with tangent planes on the midterm. Normal to a surface, tangent plane. It's a good topic. It's really pretty. For people who like to draw, it's also nice to draw them, but do you have to? No. Some of you don't like to draw. Okay, so now I say thank you for the attendance, and I'll see you next time on Tuesday. Happy Valentine's Day.